Welcome back. In this video, we're going to continue talking about rates of change, but we're going to talk more specifically about instantaneous rate of change, which means not the rate of change connecting 2 points, that secant line, which we just did in the previous video, but actually what is the slope if I were to draw a tangent line which touches at just 1 point. Now, I could derive this definition for you, but you guys are in brief calculus, so we're going to briefly just say, hey, this is the definition here. This is our definition for instantaneous rate of change. And the idea for it is this should look very similar to slope. It looks really similar to that formula we just wrote, which was f of b minus f of a over b minus a. So visually, let's think about what's going on here. Here we have some a value, and we have a curve. And that a value has a corresponding output value, f of a. So that is 1 point on the curve. And essentially, if we want to find slope, we need 2 points. But if I put a second point right here, and I find the slope between those 2 points, although it will be similar to this tangent line, which is what we are going to be interested in, it's going to be a little bit different, right? So for example, if that point was over here, this secant line is going to look different than that tangent line. So the idea here is as those points get closer and closer, as that point is very, very close to A, if you will, so close that it's essentially touching, and the distance between A and the next point, A plus H, which is H units away, is essentially 0. Those are the same points. When there's no distance between those 2 points and they're going together and becoming infinitely small, H is 0. So we're using that slope definition, and these 2 points are so close that they're the exact same point, and the limit of space, the horizontal distance between them, between A and A plus H is essentially the same thing, is 0 units away. The problem is if we tried to plug 0 into our slope function, we'd have an issue because we can't divide by 0. So we use this idea of a limit. So that's why we had to talk about limits, so that we can use the limit in our instantaneous rate of change formula. And so pulling in another picture to just really help us illustrate what we're looking at here. If we had a curve, you see this red line is the tangent line. The tangent line is only touching at this point of consideration or this point of interest. And so if I found the slope of this tangent line, that would tell me the rate of change at that exact moment. And what you can see here is the secant line, which is our traditional slope formula. The secant line is close in slope to the red tangent line, this green secant line, but it's not exactly the same. And so the idea is if I took this point and moved it infinitely closer in down here to the point where it wasn't far away at all, it was H units away, H approaching 0, then I would have the slope of that tangent line. So let's quit talking about this so much. And let's do an example. In this example, we are given a position function. So position is the location or the distance, or in some cases, height. Now, why do we use S for position and not H for position? And the reason is our definition for instantaneous rate of change that we're using already has an H in it. It's the limit as H approaches 0 of f of a plus H minus f of a over H. Now, h is in the function, so if I was using h for height or my position or my distance, it could become confusing. So oftentimes we use s. S represents the position of an object moving along some path. Now, we're asked to find the instantaneous rate of change. Well, the rate of an object moving along a path, so distance, when you find that in a rate, it's going to be that distance divided by time, or feet per second, or miles per hour. That rate is velocity. So your textbook is interchanging these two words. They mean the same thing, the instantaneous rate of change or the instantaneous velocity. So let's apply our formula. In this situation, our point of consideration, our A value, is going to be 6. So let's plug this in. And instead of F, you see here, we actually are going to have S. So S of A plus H minus S of A, all divided by H. So here we have the limit as H approaches 0. S of A plus H is going to be A plus H, quantity squared, plus 5 A plus H plus 2. So what I have, this first piece here, that represents S of A plus H. I took A plus H, plugged it in for both of my T's in the function. Now, we know what the A value is, so actually what we could plug in here is 6 plus H. All right, we're plugging in 6 plus H. A plus H, or the A value, the point of consideration, T equals 6. That's what we're plugging in. So now let's look at finding S of A. So we'll have minus this entire second function. S of A is going to be A squared plus 5A plus 2. But again, my A value is 6. I have 6 squared plus 5 times 6 plus 2. And then all of this is divided by H. So the issue here is we want to evaluate this limit, but when I go to plug in 0 for H, I have a problem. So we need to manipulate the numerator so that we can make this H cancel. So let's look at the algebra in here that we'll be doing before we plug in 0 for H. When you're working this problem, you do need to write the limit piece out every time. If I FOIL this first, 6 plus H squared, that is 36 plus 12H plus H squared. Distributing, I have 30 plus 5H plus 2. Then I have minus 36, minus 30, minus 2, all of which is over H. Once I multiply this all the way out, I'm going to see some really nice canceling, and I'm always going to expect these last terms, the terms from my F of A, to cancel out. So minus 36, I have a plus 36, that goes to 0, minus 30, plus 30, minus 2, plus 2. So again, writing this out, I have the limit as H goes to 0 of 12H plus H squared plus 5H over H. Looking at this, we should notice that 12H plus 5H are going to sum together. So I now have the limit as H approaches 0 of 17H plus H squared over H. Remember, the whole goal was to cancel that H in the denominator. And what I notice here is that both of my terms in the numerator in the top, they have an H in them. If I factor that out, I have the limit as H approaches 0 of H times 17 plus H all over H. At this point, you should see that the common factor H in the numerator and denominator will cancel to 1, and I'm calculating the limit as H approaches 0 of 17 plus h. Now that I've canceled that h, I can go and I plug my 0 value in for h. Once I plug that in, I no longer have to write limit, so I have 17 plus 0, which gives me 17. So my rate of change, my instantaneous rate of change, or instantaneous velocity, would be 17 units of measure, my units for my distance, over units time. So depending what the units were given, if this was a word problem, that could be miles per hour or feet per second. And so again, what this measurement or what this value measures or is telling us is that we know the instantaneous velocity, the rate of change at that specific moment, not over the span of time, not between two time values on the x-axis, making that secant line. Right at that one dot, we know the slope. And in this case, that dot would be at t equals 6 units. So really that's the practice that you're going to be using when you solve any of these instantaneous rate of change problems. You're using this formula. You are plugging a plus h, in this case 6 plus h in, and then plugging 6 in, your a value, finding that difference, and then manipulate the numerator to create a factor that cancels the troublesome or the problematic h in the denominator. As always, if you have any questions, please feel free to reach out and connect with me because I am more than happy to help get you on the right track.